All right, team, welcome to this explainer. Today, we are going to permanently eliminate that dreaded 2 a.m. maintenance window and master truly resilient zero-downtime delivery pipelines. I want you to step into the shoes of a lead site reliability engineer with me right now. Why? Because we're going to look at deployment not just as a way to blindly ship code, but as an absolute masterclass in failure recovery and infrastructure management. We're officially leaving behind manual toil and those brittle bash scripts, and we're moving towards automated resilience and programmatic infrastructure. It's going to be a game changer.
Planned maintenance. The system will be unavailable Saturday from 2 a.m. to 4 a.m. Oof, we absolutely do not write these apologetic downtime emails anymore. If your pipeline actually requires bringing the system down, you are essentially taxing your users for your own delivery process. Think about it. Scheduled downtime is really nothing more than self-inflicted SLA degradation. So let me show you how elite teams deploy continuously. We're talking dozens of times a day without dropping a single user request, and definitely without sacrificing their weekends.
So here is our SRE blueprint for today. We're going to cover the downtime problem, readiness probes as our safety net, deployment strategy trade-offs, Canary releases for measured risk control, GitHub actions for automated rollbacks, and finally, audit trails and environment gates. Let's just dive right in. Section 1, the downtime problem. Let's look at exactly why naive deploys fail and why that maintenance window exists in the first place.
Basically, a naive deploy stops the old version way before the new one is actually ready. Under the hood, this happens when Kubernetes sends a SIG-term signal to the old pod before the new pod's application loop has fully initialized. And that sequence right there creates a massive downtime gap. We're talking seconds or even minutes, where the ingress layer is just throwing ugly 503 service unavailable errors right at your users. So our absolute overarching rule for zero downtime is this: never, ever stop serving traffic until the new version is actively taking requests. The old replica set stays at full capacity, the new replica set gets ready. We switch the traffic over, and only then do we scale down and kill the old pods. No gap, literally zero downtime.
Section 2, readiness probes, the safety net. To pull off this zero downtime transition, Kubernetes needs to know exactly when a pod is actually safe to receive traffic. Enter the readiness probe. This is the fundamental gating mechanism that strictly prevents Kubernetes from sending traffic to a pod until it successfully passes a health check, like, say, returning a solid HTTP 200 on a health endpoint. Without it, Kubernetes just blindly sends traffic the very second a container starts, and that's usually way before the application has actually warmed up, compiled its assets, or even connected to the database. But with a readiness probe properly configured, that downtime gap is completely eliminated because the load balancer actively waits for that HTTP 200 success signal. Now, to prevent false positives during that warm-up phase, we also carefully configure our initial delay and period seconds. This is absolutely crucial for automated failure rollbacks, too. If an automated rollback fires, the readiness probe ensures we don't route traffic back to a standby pod that isn't actually ready to save us. Section 3, deployment strategy trade-offs. Listen closely here, team, because senior engineers care deeply about trade-offs. It's all about balancing your infrastructure costs against your failure recovery speed. Junior engineers usually just want to push code, right? But senior engineers design for the exact moment that code fails. Notice how blue-green gives us instant, sub-second failure recovery, but it costs exactly 2 times in pod capacity because you're running 2 full, identical environments. On the flip side, rolling updates are incredibly cost-efficient at 1x capacity, but they can literally take minutes to roll back since you're replacing pods one by one. And then Canary sits right in the sweet spot in the middle. It gives us measured risk with just a tiny bump in infrastructure cost, roughly 1.1x, because you're just spinning up a small parallel replica set alongside the primary one to handle that initial test traffic. Let's look at the actual config for those cost-efficient rolling updates. By setting max surge to 2 and max unavailable to 0, we guarantee that we never drop below our desired healthy pod count during the deployment. The Kubernetes deployment controller uses these exact variables to manage the underlying replica sets and strictly enforce that budget. It essentially allows us to temporarily burst up to 2 extra pods just to bring the new version online, but the availability literally never dips. This should absolutely be your battle-tested default for routine updates when your infrastructure budget is tight. Now, let's explore how blue-green solves that rollback speed problem. When we absolutely need instant rollback and we actually have the infrastructure budget to support 2x pod capacity, blue-green is the way to go. We deploy our new version to an idle green environment and run all our smoke tests safely in total isolation.
Then, when we're 100% confident, we switch the service selector in a single atomic API call. This simply updates the label selector on the Kubernetes service object, like changing it from pointing to @version v1 straight to @version v2. This instantly updates the endpoints for the load balancer. Boom, 100% of traffic moves instantly. And the best part? If something breaks, one single command puts everyone safely back on blue in under a second. It's magic.
Section 4. Canary. Measured risk control. Now, what if the change is highly risky, like a massive algorithm change, or maybe a brand new pricing tier? We definitely don't want to expose all our users to that at once, even for a split second. So let's move to canary releases. Think of it like coal miners carrying actual canary birds down into the mines to detect poison gas. We route a tiny fraction of real production traffic, say just 10%, to the new version. To manage this super precise traffic weight splitting, we'll typically rely on an ingress controller like Nginx or a service mesh like Istio. Then we watch our metrics like a hawk. We're comparing the error rates and P99 latency of our canary straight against our stable pods. If the metrics hold steady, we slowly expand the blast radius, 25%, then 50%, and finally a full 100% cutover. But if those metrics degrade, we abort immediately. And the beauty is, only a tiny fraction of our users ever even saw the glitch. Section 5. GitHub Actions Automated Rollbacks. This right here is how you get to sleep through the night while on call. As your mentor, I want you building systems that literally fix themselves. Let's build hands-free automated failure recovery right into our deployment pipelines using GitHub Actions. So after our traffic switches in a deploy, we automate a 5-minute observation window. We use a very specific Prometheus PromQL query to act as our automated eyes. We're taking a rate of 5xx HTTP errors over a 2-minute rolling window, and we check if that rate crosses a 1% threshold. We are not sitting around waiting for a user to complain on Twitter. The system is actively, mathematically hunting for degradation. The really crucial point here is that if that Prometheus query detects an error spike and fails the check, a GitHub Actions if failure block instantly takes over. It executes a kubectl-potch service command. The action catches that failed exit code from the Prometheus check and patches the service selector directly back to the stable blue slot, executing the rollback natively right in the cluster. This entire recovery executes in milliseconds, completely hands-free while you're off grabbing a coffee. Your pipeline caught the error and healed the entire system before a single alert even buzzed on your phone. How cool is that? Section 6. Audit Trails and Environment Gates. Finally, true SRE magic isn't just about clever automation scripts. It's also heavily about security, compliance, and covering our assets in production. Before a single byte of new code ever hits our production clusters, GitHub Environment Protection Gates step in. This mechanism enforces a mandatory manual human approval step directly in the UI. When triggered, it intercepts the deployment workflow, actively preventing the action runner from obtaining the necessary OIDC tokens to authenticate with the Kubernetes cluster until that physical UI button is clicked. And guys, this isn't just corporate bureaucracy. It gives us an immutable audit trail that completely satisfies SOC 2 compliance. It ensures a strict separation of duties between the engineer who wrote the code and the release manager who authorized it, completely preventing unauthorized or accidental production changes. So, as you go off and design your next pipeline, I really want you to ask yourself this. Are your deployment pipelines built on hope, or are they engineered for hands-free automated failure recovery? Because hope is writing apology emails at 2 a.m. True resilience is zero-downtime strategies, readiness probes, and automated failure rollbacks. Join us in the next explainer to see how Argo CD takes this GitOps automation even further, removing manual commands from the pipeline entirely. Until then, build systems that never sleep so you can.